So welcome to the third lecture on information black holes and the holographic principle. And today we're going to look at black hole thermodynamics, or at least what you might call black hole dynamics. And to start with that, let's remind ourselves what the Schwarzschild black hole looks like. It's this line element here where we have the Schwarzschild radius, which depends on the mass m. So m is the mass parameter. And this is a spherically symmetric static black hole spacetime, which obviously is characterized by this parameter and only this parameter, apart from natural constants like Gn or c, the Newton constant or the speed of light. And other relevant black hole solutions that had been derived later on are the static and spherically symmetric Eisner-Nordström black hole with mass m and electric charge q, the stationary axially symmetric Kerr black hole where you have mass m and angular momentum j, and then essentially the synthesis between them is the stationary axially symmetric Kerr-Newman black hole, which has mass m, electric charge q, and angular momentum j. And in fact, it can be shown. I recommend this textbook here for details that this kind of Kerr-Newman black hole with these three parameters, ignoring outlandish possibilities like magnetic charges, is the most general solution describing a stationary axially symmetric black hole in the Einstein-Maxwell theory. So Einstein gravity coupled to Maxwell electrodynamics. And this is an expression of the more general no-hair conjecture for four-dimensional Einstein-Maxwell theory that the end state of black hole formation essentially sheds most of the initial information. So you have a star, let's say, that star can have all kinds of properties. Its spectral class and its chemical composition, what's the relative abundances of all the different chemical elements in that star. And when that star collapses, it forms a black hole. And that black hole, I mean, it may have some perturbations that settle down very quickly. They die out exponentially like the ringing of a bell. And then what you're left with essentially is such a black hole of the Kerr-Newman type, which is described exactly just by three parameters: mass, angular momentum, and charge. And these black hole solutions are a bit complicated, and they won't be, the exact form of them won't be so relevant for most of the rest of the lecture, but I actually find them very interesting, and I wanted to spend a little bit talking about them. So again, this is the Schwarzschild black hole. As a reminder, you have this one parameter here, essentially the horizon radius RS, depends on the mass m, and this is what you remember is the Penrose diagram. You have this singularity here, which is a space-like singularity, meaning this kind of curve is like you could see it as an equal time slice. You have this infinity structure here with null infinities, which is characteristic for an asymptotically flat spacetime, as I said, and you have these diagonal lines, which are the event horizons. So there's essentially only one event horizon here. And you have these kind of two universes that cannot be traveled in between by a causal observer. That's the Schwarzschild black hole. And if you go to the Kerr-Newman black hole, what you see is this line element. These are the so-called Boyer-Lindquist coordinates. Obviously, there's a number of parameters here. Essentially, you have q, the charge, and you have the angular momentum j. And in the case where charge, we have not only this metric, but on that metric, we also have an electric field, which is given by this potential here in this form. And obviously, this is much more complicated, and people can work out the Penrose diagram for these kind of space-times. So let's have a quick look at them. They're given here. These figures are all from the very nice textbook by Hawking and Ellis. So on the left side, we have a Penrose diagram for the charged non-rotating black hole, Reisner-Nordström, in the non-extremal case. What that means is that the charge compared to the mass satisfies a certain bound. Essentially, the charge is less than the mass in natural units. And what you see here, focus on this part of the figure first. This is essentially what we know and expect from asymptotically flat black holes. So we have these null infinities here. This is essentially the outside of the black hole, our universe. And these dashed lines here, that's the event horizon. In this case, it's called the outer event horizon, because these black holes can in general have outer and inner event horizons. So these are the outer event horizons. Nothing that happens behind this event horizon in the regions labeled 2 or 3 can send a signal to our infinity. There is still this kind of parallel universe here in this region. And obviously, compared to the Schwarzschild black hole, the diagram changes here, because here in the Schwarzschild case, there would be a space-like singularity. But in the charged case, what you see is that there's this region, and you have time-like singularities here. So this line is r equals 0, and this line, this line here is r equals 0, and the space here is the interior of the black hole. So what you see is you have these dashed lines here. Those are the so-called inner horizons, or Cauchy horizons. They are called Cauchy horizons because they are essentially a boundary of predictability. So suppose we have kind of fields or matter fields, and we know the initial conditions on that matter fields on this vertical line here, this one. If we have initial conditions here, we can calculate the evolution of fields and particle motion forward in time throughout these regions here up to these lines, the so-called Cauchy horizon. So this is what we call a Cauchy surface. And if we wanted to continue the evolution beyond that, we would have a problem, because now that the singularity is time-like, theoretically information from the singularity could come here and affect particle motion in that region 3. So we cannot predict what happens in region 3 based on initial data on this surface. That's why it's also called a Cauchy horizon. And there's a question in the chat. 1 second. Yeah, so what happens is the following. If you stand on the surface of a collapsing body, like a collapsing star, you can be pretty sure that the black hole is actually formed, because the event horizon is not locally observable, but the singularity can be reached by an observer that moves with the matter of the collapsing star in finite time. So that's pretty strong indication that, in a sense, from an observer falling into the black hole is real. Now, from an observer standing outside, you have the following problem. You never see anything really entering the black hole because of the infinite time dilation. So when a star collapses and you look at the surface of that star, like suppose there's a sunspot, and you want to track how that sunspot moves during the collapse process, you never really see it vanishing behind some kind of curtain. Theoretically, a photon from that sunspot could always reach you. But there's 2 things that you need to consider here. First of all, suppose there was a clock on that sunspot, there's a finite time beyond in the frame of that of the surface of the star, where it crosses the event horizon. So if you look at a watch on the surface of a collapsing star as it collapses, there's a certain time that you will never see that watch go beyond, which just means that you only observe a finite interval of the life of that watch or clock. Also, obviously, this infinite redshift means that any photon that would come from there will be increasingly redshifted. So in a sense, it's not like you see images of the surface of the star frozen on the horizon. Those are redshifted exponentially, and very soon what you see there is indistinguishable from a black hole as described by the exact Schwarzschild solution. So I hope that answers the question. Maybe I didn't quite make it clear. Right, very good, thanks. Good. So let's come back to the Reisner-Nordström black hole. So as I said, these inner horizons are Cauchy horizons because they form a boundary of how far we can predict physics based on initial conditions that are given in our usual universe. Beyond that, our predictions would depend on how the singularity might interact with particles or observers here. And this is something that we really cannot calculate because our physics breaks down at the singularity. But curiously, if you're an observer here, remember how these Penrose diagrams work. An observer is someone who can travel essentially at any line that is sloped less than 45 degrees to the vertical. So an observer could be traveling around this curve that I'm tracing out with my cursor. He would fall into the black hole. He would cross the Cauchy horizon, but because the singularity is time-like, it can be avoided. So this observer could theoretically emerge from this white hole region of essentially a second copy of what we saw before. This here is essentially a copy of this. So someone who falls in a black hole and avoids the singularity would emerge from a white hole in a new universe, so to say, according to this maximal extension of the geometry. But of course, I already discussed that these eternal black holes are highly idealized mathematical solutions. This is not what you would expect from an astrophysical black hole. In fact, there are certain stability considerations concerning these Cauchy horizons related to a process that's called mass inflation. Essentially, the idea is if matter actually falls in this black hole, that kind of disturbance from the mass of that matter would cause the singularity to shift from here onto the Cauchy horizon, so that you cannot go beyond this Cauchy horizon without encountering a singularity. That's what you would expect. And what you see here is the Kerr black hole. Oh, sorry. One second. Yes. What you see here is the Kerr black hole. That's a rotating non-charged black hole. The structure is very similar. This is kind of the asymptotic flat space portion of the diagram. This is the event horizons, the diagonal lines here. Here you have this kind of parallel universe. Here you have interior horizons. This is interesting because here you see this line is r equals 0. This is where the singularity is. But as you see, the space-time is extended beyond that. And the reason for that is that in the rotating Kerr black hole, the singularity is actually a circle. So you can avoid it and essentially travel through it, and then you end up in another asymptotic flat region, which is characterized by a naked singularity, which can be seen from everywhere here. So this is the mathematically maximally extended and very much idealized rotating black hole. There's also closed time-like curves in this region. So theoretically, if an actual space-time was described by this, then you could, travel through time behind the horizon of a rotating black hole. But of course, again, for the same reasons, it's expected that the space-time inside of these horizons is highly unstable, and that the perturbation by like the gravity of matter falling into this black hole would be enough to, in a sense, move the singularities forward. And here you see the so-called extremal limit, where the angular momentum is set to a very specific value. In that case, the structure changes a bit. And we will come back to the extremal limit later a little bit. So this is essentially these diagrams for Penrose diagrams for the Reise-Nordström and Kerr black hole. And obviously, nothing that happens inside of these event horizons should be considered to be of astrophysical relevance. It's very likely that this is just a mathematical idealization. But the Kerr black hole also has very interesting features outside of the horizon, namely a so-called algosphere. The idea behind this is that the black hole rotates, and this causes a frame dragging effect, which means that if you go too close to the black hole from a certain radial distance, even if you're still outside the event horizon, you cannot stand still. You have to travel along the rotation direction of the black hole around it. So here we see this kind of diagram. This is the symmetry axis around which the black hole spins. You have this, here you have an equatorial plane. You have this kind of ergosphere. The ergosphere extends the most from the horizon at the equatorial plane. And at the symmetry axis, the ergosphere touches the event horizon. The ergosphere is the part of the space inside of which you cannot stand still, where this frame dragging is so strong that you cannot remain at fixed angular coordinate. Then you have the outer event horizon. You have the r equals r minus, that's the inner event horizon or Cauchy horizon. And here you have this ring-shaped singularity. And here, essentially, what you see in this picture here is looking from the top onto the equatorial plane, which is essentially these kind of circles here. So every point here that you see stands for an event, let's say, and the circle stands for a section of the light cone, let's say 1 second after the event happens. And far away from the black hole, you can see that from the event, signals after 1 second, let's say, can go into every direction. But the closer you get to the black hole, the more these kind of circles are shifted towards the black hole. That's this kind of tilting of the light cones that we saw last lecture. But because of the frame dragging, the light cones are also tilted to the side. So the black hole rotates in this way. So the ergosphere is the place where first the circle here is shifted from its original point to the side. If you start at this point and you send a signal, you can still send it to larger radial directions. So you are still outside of the event horizon, but you cannot send it to against the axis of rotation. The signals are in a sense frame dragged in the direction of the rotation. And the closer you get to the black hole, the more this effect happens, and the event horizon is precisely the point where these circles are also shifted inwards so much that you cannot send a light ray to larger radial coordinates anymore. And then here you have the inner event horizon, and this is the ring singularity. So, well, this is a short discussion of these features of the Kerr black hole, and especially this kind of ergosphere is very relevant in the astrophysical context. So if you're dealing with black holes from an astrophysical point of view, this is something that you should keep in mind, or that hopefully you know. Good. But let's come back to the physics of all of this, or the theoretical physics of all of this. Remember, we have these three parameters here: m, q, j, the mass, the charge, the angular momentum. And of course, there's also geometric properties of the black hole, like the size of the event horizon, the area of the event horizon. So if we vary these parameters, how do they change? The area of the event horizon is not independent of these, but you can actually show that the following law holds. If you change the mass, the angular momentum, and the charge by like dm, dj, dq, then the change in the surface of the event horizon, the surface of the induced metric, obeys this formula. So masses, I set the speed of light to 1, so by equals mc squared, the mass is essentially the energy here. The A is the area of a section of the event horizon. We are setting Newton's constant to 1 also. J is the angular momentum, Q is the electric charge. And then you have these parameters here. K is the so-called surface gravity at the horizon. Omega is the angular velocity of the rotating black hole. And phi is the electrostatic potential. And this is very similar to the first law of thermodynamics, of course, where the energy changes like this. These, like the dependence on things like charge or so, is the same. And here we have temperature times the change in entropy. So these laws are essentially identical if we identify S to be some constant times the area, and T, the temperature, to be some constant times the surface gravity. And I've introduced this parameter alpha here because so far we don't quite know how to fix these constants, because I mean it's a product. We only know that the product T times ds would have to be identified with the product kappa over 8 pi times dA for this to make sense. But we could shift this factor between T and S. So, well, let's investigate this further. First of all, let me give you the definition of what the surface gravity is. So remember, last lecture we talked about how to define the boundary of a black hole, and there are three different kinds, proposals, that happen to be identical for the Schwarzschild black hole and also the Kerr-Newman black hole, but don't have to be identical for more general things like time-dependent black holes. And these three definitions are the event horizon, which, as you remember, is kind of defined as a feature of the causal structure. There was the marginally trapped surfaces, which we talked about also in the exercise sheet. And the third definition was the so-called killing horizon. If you have a stationary black hole, it means, by definition, there's a time-like killing vector field. Essentially, that means your space-time is invariant under time translations. Now, there's a technical difference between the terms static and stationary. Both have a time-like killing vector field. In the stationary case, that's enough. In the static case, there's an additional condition that the time-like killing vector field has to be hypersurface orthogonal. That's a bit technical. I was once told there's a good way how to remember the difference. A static space-time is one that is the same at any time. A stationary space-time is one that does the same at every time. Essentially, the charged and the Schwarzschild black hole, non-rotating, they are static. They are just sitting there. They are the same at any time. The rotating black hole, you could imagine it like a rotating body. It does the same at every time, namely rotating, but if you imagine it like a body, you would have to take into account the rotation from one time to the other. So that's the kind of quantitative rule of thumb, but what the difference between a static and a stationary state is. Not only black holes, states in any kinds of situation. Anyway, there's always a time-like killing vector field for these black holes. At least the killing vector field is time-like outside of the black hole in the asymptotically flat region. And on the horizon, the killing vector field, on the killing horizon, the killing vector field is a null vector field. And then you can define the so-called surface gravity on that horizon by this equation, which is commonly given. There's an equivalent reformulation of this, which has this form. And for the Schwarzschild black hole, kappa is essentially 1/4 times n, m times these constants. Good. So let's quickly check this first law for the Schwarzschild black hole. The Schwarzschild radius is 2m, and you equate energy with mass, so equals m. Kappa is 1/4m. A, the surface of a section of the event horizon is 4 pi r s squared, and that's 16 pi m squared. And so kappa over 8 pi times dA is precisely this, and it's dm. If you vary m by an infinitesimal step dm. So that's the analogy between the first law of thermodynamics and the first law of black hole mechanics or black hole dynamics. And now the question is, are there analogs of the other laws of thermodynamics in the laws of black hole mechanics? And of course, it's very well known that the answer to this is going to be yes. So let me explain. First of all, the zeros law. It can be proven for black holes that the surface gravity kappa is constant everywhere on the killing horizon of a stationary black hole. It does not vary along the null rays that generate the horizon. That's trivial, and it does not vary along spatial sections of the event horizon. Like, it does not vary from one light ray to another. It's just constant. And this is, in a sense, an analog result to the Zero's law of thermodynamics. If we identify kappa with temperature, namely the Zero's law usually states if A is in thermal equilibrium with B, and if B is in thermal equilibrium with C, then A is in thermal equilibrium with C. And this postulate is essentially important for the definition of temperature in thermometers as a whole, because suppose this were not the case, and I have a thermometer and I plug it in one cup of tea and it shows me a certain temperature, and I plug it in another cup of tea and it shows me the same temperature. If that law wouldn't hold, I couldn't determine that these two cups of tea have actually the same temperature, because there might be something about the interaction of the thermometer with each cup of tea that is different in a sense. But the idea that thermal equilibrium is equivalence relation means that, I put in my thermometer in a heat bath, let's say, and I wait until it's in equilibrium with the heat bath. So if the thermometer shows me a certain temperature, that is the temperature of the heat bath. That's essentially what this law enables us to define, and the analog for black holes is this, namely that essentially the horizon of these stationary black holes is in thermal equilibrium, with each part of the horizon is in thermal equilibrium with the others. And then famously there's the second law, which was proven by Hawking, which says in classical processes, which involve matter fields that satisfy the weak energy condition. So we are looking at cases where, let's say, we throw matter into black holes, but what kind of matter? So we know we can couple Einstein's equations to all kinds of matter fields, like we can couple it to a scalar field, we can couple it to Maxwell electrodynamics, we can couple it to energy momentum tensor that would describe a dust of matter or fluid of matter. But in general relativity, when you want to prove theorems, it would be tedious to go through the list of all possible matter fields and check that something is satisfied if Einstein gravity is coupled to that specific matter field. Instead, what you do is that you assume a certain property that you think is reasonable for any kind of matter field, and then you prove your result only from that assumption. So as you know, Einstein's equations coupled the Einstein tensor to the energy momentum tensor. So it makes sense that you look at generic features of the energy momentum tensor of physical matter, like features that all physical reasonable matter types have in common. And one of them is that you expect the energy to be positive. And what does that mean? Well, if you have an observer who flies through your space-time on any curve, the energy that this observer measures of the matter field is essentially given by the contraction of the energy momentum tensor with the tangent vector of the world line of that observer. And for a reasonable observer, that tangent vector can be any light-like vector, any vector that satisfies this kind of condition, i.e., which is inside of the future light cone. So we propose this energy to be positive or non-negative for any plausible observer. That's the so-called weak energy condition. There are other energy conditions that can be used in general relativity to prove theorems, like the null energy condition or the strong energy condition. Well, there's a whole story to how reasonable these energy conditions really are, and some energy conditions are stronger, but they may be violated by certain matter fields. Other energy conditions, like the null energy condition, are more weak and hence satisfied by a larger class of matter fields, but then it's harder to prove results only assuming that condition. Anyway, Hawking in his result assumed a weak energy condition, and he obtained the result that the area A of the event horizon of a black hole does not decrease in time under any kind of process. Like if you saw in matter, it can only increase. And similarly, in the collision of two black holes, the area of the resulting event horizon exceeds the sum of the initial event horizon areas, according to this form. And this is known as the area theorem. And if we want to insist on this equivalence between the thermodynamics and black hole mechanics, for which we need to assume that this area is kind of an analog of entropy, then this makes sense because, of course, this monotonicity is similar to the second law of thermodynamics, which states that entropy cannot decrease. And again, I'm not going to go through the details of the proof. Let me just say this is a statement about the event horizon. And philosophically, what's being employed in proving this is this feature that I discussed earlier, last lecture, that the event horizon is essentially defined backwards from the future. So you have the future here, and the event horizon is starting at this point and calculating backwards in time the path that the last light ray took, which reached this point. That's the event horizon. And because of that, you know that any light ray that is on the event horizon here cannot have an endpoint anywhere before reaching infinity. Like it cannot leave this and fall into the singularity. It cannot end on a collision point with another light ray. And this essentially gives you a certain mathematical structure of the event horizon that leads to the result that the area cannot decrease if matter satisfies this condition, the weak energy condition. So the fact that this feature is, in a sense, defined in such a backwards way in time is the key to obtaining this result. Yes. So that's the second law. And finally, we find the third law. This was only conjectured in this paper here, where the 4 laws were proposed. But the third law of black hole thermodynamics states that it should be impossible by any procedure to reduce the surface gravity, which is our analog to temperature, to 0 by a finite sequence of operations. And again, by this analogy with thermodynamics, where kappa stands for a temperature, this corresponds to a specific formulation of the third law of thermodynamics, namely that it's impossible to reduce the temperature of any system to the absolute 0 in a finite number of operations. There's different formulations of the third law of thermodynamics, and this one is the one that fits to the black hole case. There's others where it says that you can't, like there's another formulation that says that at 0 temperature, the entropy of any object is a universal constant that can be set to 0. That's not quite the case for black holes. For example, the Kerr-Newman black holes, which are charged and rotating, they can have 0 temperature but finite area and hence finite entropy in the so-called extreme limit, where you make the charge and the angular momentum as big as you can without destroying the event horizon. That's this extreme limit, where also the Penrose diagram takes on a very special form, as I showed you. Essentially, what the third law suggests is that this bound cannot be crossed. So suppose you have a charged black hole or a rotating black hole, and you want to overcharge it or overspin it by throwing charged particles in there, or throwing massive particles in there in a slanted way such that it increases the angular momentum. If you start with a non-extremal Kerr-Newman black hole and you do these kind of processes, you should never be able to reach this exact value, and you should never be able to cross this value. That's important because if you were to exceed this bound here, the event horizon would disappear altogether, and you would be looking at a space-time that has a so-called naked singularity, where the curvature singularity is not shielded from asymptotic infinity by an event horizon anymore. And that would violate the so-called cosmic censorship, according to which we expect that curvature singularities are always hidden behind event horizons. So this third law in this specific formulation is very important from that point of view. And in fact, Werner Israel proved a formulation of this third law a while later. A non-extremal black hole cannot become extremal at a finite time in any continuous process in which the stress energy tensor of matter stays bounded and satisfies the weak energy condition. So again, this weak energy condition plays a role here as a reasonable assumption that we expect should be satisfied by almost any classical matter. So to summarize the 4 laws of black hole dynamics, which are, suggest a certain similarity with thermodynamics, read in the following way. The 0th law, kappa is constant on the killing horizon. The 1st law, changes of these parameters are related in a certain way. The 2nd law says that the area can only increase in classical processes satisfying these energy conditions. The 3rd law says that the absolute 0 of the temperature kappa is not attainable. Okay, and as I said, together these laws suggest an analogy between temperature and surface gravity, and also between entropy and horizon area. And And you could leave it at that. And originally, people didn't quite know how seriously to take this. You could say this is just a funky analogy, but there are essentially two results that suggest this is more than just an analogy, and that what we are seeing here, genuinely is the thermodynamics of black holes. And those two results are the following. First of all, a proportionality between a genuine entropy and the horizon area had already been conjectured by Bekenstein in thought experiments. Essentially, what he considered is the idea that you throw a very entropic object into a black hole. It would seem that the entropy of the universe decreases. The reason for that is that the no-hair conjecture suggests that all of these black holes they are very simple. They have, in a sense, simple macro states, if you want to view it from a thermodynamic perspective, and they are described by very few parameters. So there's no room for them to encode entropy, in a sense. At least that's what it seems like from the classical general relativity point of view, unless you say that the area of this horizon is another form of entropy. However, his thought experiments were not enough to fix this prefactor. It might still be anything. In fact, his original suggestion was a slightly different value than the one that we are going to find in the end. And then there was this famous result by Hawking about Hawking temperature and Hawking radiation, according to which black holes actually radiate like physical bodies at a temperature that is given in his calculation exactly by kappa over 2 pi, which now fixes this parameter alpha that I carried along to be 1. So alpha is 1 here and here. And this so-called Hawking radiation can lead to the evaporation of black holes because it carries away energy of it. So this suggests that there is a genuine black hole thermodynamics described by these 3 laws. Yeah, that's a good question. Second law. So it says in classical processes involving matter fields that satisfy the weak energy condition. So the Hawking radiation is a quantum process. And in fact, I mean, whenever we discuss these energy conditions, they are not theorems. They are, in a sense, assumptions. And they can be violated. For example, the best example of a violation of the weak energy conjecture would be the Casimir effect, which is a quantum field theory effect where you have 2 parallel plates and they kind of affect the quantum vacuum fluctuations, and it leads to a negative energy locally between the plates. So locally, this energy condition can be violated by quantum effects. It's a very, very important research direction to find energy conditions that are robust even under quantum effects, and that can not only be conjectured but even proven. And there's different ways that you can do this. For example, there are so-called averaged energy conditions, where you say, where you are don't making a statement about the energy on a certain spacetime point, but you say, if I have a certain curve through spacetime, the average of energy along that curve has to be positive or negative. So there's the average null energy condition and things like that, which essentially means that a negative local energy is fine if it is offset by enough positive energy elsewhere. So this is a very, very fascinating research direction, you know, investigating energy conditions. How reliable are they? How can they be violated? Can they be violated in like physical situations or only in very unphysical situations? In the case of Hawking radiation, that's a quantum effect, and the quantum fields can lead to a violation of the energy condition there near the horizon. Okay. Where was I? Yes, here. So, okay, that's the thermodynamics of the Schwarzschild black hole. These are the parameters, the size, the temperature, and the entropy. So here's a bunch of bullet points that you should remember. First of all, heavy, i.e. large M Schwarzschild black holes are large because it scales with M, and they have a lot of entropy because it scales with M squared. But they are cooler because the temperature scales with 1 over M, and hence radiate or evaporate slower. And the lifetime of an evaporating black hole can be estimated to be of order m to the power cube. Calculating the exact lifetime is a bit complicated because the luminosity will depend on the temperature. For very low temperatures, the only kind of particles that can be radiated are massless particles like photons and gravitons, because the average energy of a quanta of Hawking radiation will be very, very low because of the low temperature. If the temperature is high enough, such that the average quanta of an energy of a radiation particle exceeds, let's say, the mass of an electron, then electrons can show up in the Hawking radiation. And gradually, as the temperature gets higher and the energy of a average quanta of radiation gets higher, more and more species contribute to the evaporation process. But for most black holes, especially in an astrophysical context, only the massless species really add to the radiation, and that also has the effect that like charged black holes, let's say, cannot easily radiate their charge away. Like if you have a charged black hole, it could lose charge if in its radiation electrons can appear. But if the temperature is too low, then electrons are ruled out because you would have to generate their mass in the Hawking radiation. And if the temperature is too low, the energy of the quanta of Hawking radiation is too low, so electrons cannot be excited and the charge cannot be radiated away. So these black holes tend towards the extreme limit. But obviously, as the third law says, they could never reach it exactly. There's actually a very nice rule of thumb that I came across. The average wavelength of an emitted photon or particle will be of the order of the size of the black hole. And the consequence of this is that even if there was, let's say, a primordial black hole, which is very, very hot and radiates a lot of Hawking radiation, such that you can see it with your eyes, you would never be able to see a sharp picture of the event horizon or whatever, the way that you see a sharp picture of the surface of the sun if you look at it in a telescope, which you shouldn't do with your eyes, but obviously astronomers have telescopes that are constructed to make pictures of the sun, and you see all the sunspots and whatnot. You could never have a you could never have a sharp picture of a black hole from its Hawking radiation, because the wavelength of the average quanta of radiation is always going to be of order of the event horizon. So you could never have a well-resolved picture of the black hole from its Hawking radiation. It's always going to be fuzzy. It's kind of an interesting result. And here's I mean, obviously, I'm a theoretical physicist. I usually set all these constants to 1 here. I rarely ever plug in astrophysically relevant numbers and calculate what comes out. But here's one little fact that I know, and which I always find fascinating. If you wanted to have a black hole with a temperature of about the same as the cosmic microwave background, which is 2.7 Kelvin, very, very low, that black hole would have to have a mass of half the mass of the moon, half lunar mass. Any black hole that is more massive than that, like all the astrophysical black holes known in the universe, is going to have a lower temperature than the cosmic microwave background. Orders of magnitude lower in the case of the stellar black holes, or even the supermassive black holes in the centers of galaxies. So these kind of black holes, even if you would prevent all infall of mass, like dust or gas, these black holes still wouldn't really evaporate in our universe nowadays, because they would still increase in mass by absorbing microwave background radiation. They would gain more energy from absorbing radiation from the microwave background than they would lose by their own Hawking radiation. So if you want for such a black hole to even start radiating and decaying, you would have to wait for the expansion of the universe to dilute the microwave background so much that even that temperature is lower than the Hawking temperature. Otherwise, I mean, to phrase it differently, right now we are in an era of the cosmos where most astrophysical real black holes are not in thermal equilibrium with the microwave background. They are cooler than that. They get warmed by the microwave background. I always found that a very neat thing to know. And these black holes have negative heat capacity. The more energy they lose through radiation, the hotter they become and the more they radiate. So assuming no matter infall, that's kind of a weird little feature of black holes in asymptotically flat space-times. Which means that if you calculate this kind of evaporation process, it starts slow, but it gets faster and faster towards the end. And the presence of this black hole radiation implies the black hole information paradox that we're going to look at more closely in the next lecture, namely what happens to the information that fell into a black hole. Obviously, if it wasn't for this radiation, then this identification of entropy with the area would be sufficient to kind of answer the question, what happens to the information that falls into a black hole? Well, it's in a sense encoded in the entropy of the horizon, which increased when that object fell in. But now that black holes can evaporate through these quantum processes, and they might even disappear, the question is, where does this information then go? And as I said, we're going to look at the black hole information paradox more in the next section, next lecture, sorry, next week. The next part of the lecture is going to be about a little trick that you can do, which is very interesting, namely looking at black holes in the Euclidean space, where instead of a time direction, you complexify the time direction. But before we look at that, are there any questions about the first part of the lecture? No questions? Okay, so let me go on with Euclidean black holes. Here's the thing. The calculation that Hawking did about his black hole evaporation was quite complicated and done in a space-time describing the formation of a black hole from collapse, which is what you expect in an astrophysical setting. But the temperature that he obtains for the late-time radiation is just this. And this is independent of the precise details of how the formation and collapse process looked like. So this seems to be, in a sense, a feature of the Schwarzschild solution in general, and not just of these collapse scenarios. You can understand this by doing this analytical continuation to Euclidean time, where essentially you define a time coordinate tau, which is I, the imaginary unit, times t. And you're going to do that on the exercise sheet for next week for our BTZ black hole, which is very simple. In general, what happens also for the Schwarzschild black hole is that you go from this kind of conformal diagram in the Lorentzian case. Sorry. You go from this kind of diagram in the Lorentzian case to this kind of diagram in the Euclidean case. So the Penrose diagram for the Euclidean black hole looks like a circle, as it turns out, where the point in the middle is this point here where the event horizons cross. Remember, that was called the bifurcation surface. essentially, this Euclideanization cuts off the entire part of the spacetime inside of the event horizon. And this section here would be identical to this section here, because these two diagrams fit together along the surface where t equals 0, where also tau equals 0. And okay, so it turns out this thing gets a circular shape, where the Euclidean time tau has to be identified with a period of exactly 8 pi m, which, as you remember, is 1 over t. So the periodicity in Euclidean time is related to 1 over the temperature. In the Kruskal coordinates, this is entirely obvious. In the Schwarzschild coordinates, you might be confused, like if you replace t by minus I tau, why does tau have to be identified periodically? Or why does it have to be this period? Well, if you would choose any other period, that would be essentially like cutting out a wedge of this circular diagram here and gluing it together, such that there would be a conical defect, like a deficit angle. And this would lead to problems. So this period is uniquely selected by the requirement that there should be no conical defect or deficit angle in the middle of this diagram. Good. And so the periodicity in Euclidean time is related to the temperature via this relation for a simple reason. This is a bit technical. Suppose you have a Hamiltonian. Then, of course, if you want to calculate the time evolution, that's given by a unitary operator like this. And from a QFT point of view, the amplitude to go from a state phi at phi 1 at time t1 to a state phi 2 at time t2 is given by this kind of matrix element, where you have this evolution operator wedged between phi 2 and phi 1. And this is given by this kind of path integral. The path integral is, here you have the action of your theory, and here you integrate over all field configurations which obey these boundary conditions. So here you have the space. This is your Cauchy surface at time t equals t1. This is your time surface at t equals t2. Here the field is fixed to be phi equals phi 1, or the state is fixed to be this. Here your fields are fixed to be in this state, and the path integral is over all the paths in the field space that connect these two boundary conditions. If you go to the Euclidean time now, the following thing happens. T2 minus T1 is minus I beta, where beta is the period of Euclidean time. And the periodicity means that we set phi 2 equals phi 1. So essentially we take these two surfaces, the initial time surface and the final time surface, and we glue them together because of the periodicity of time in Euclidean space, and we get this circle. And because we glue them together, we need to make sure that the boundary conditions are adequate to that. So for the gluing to work, this field configuration needs to be the same at the initial and the final time. But it only needs to be the same. It doesn't need to be specified to be anything. So not only do we set phi 2 equals to phi 1, we also sum over a basis of all the phi's, all the possible field configurations that could be on this gluing surface. That means that this expression, which is adequate for the Lorentzian case, we replace by this expression, which is adequate for the Euclidean case. And you see, essentially, this is just the trace of this kind of operator here, where we have e to the minus beta times h. Beta is this period in Euclidean time. And that is the thermodynamic partition function at temperature t equals 1 over beta. Beta is the inverse temperature. So this is how you can kind of define thermodynamics in quantum field theory and quantum mechanics, by defining this partition function. And in the settled point approximation, where we have a solution to the equations of motion, we essentially assume that this kind of path integral is given simply by evaluating the action, now the Euclidean action, on that solution, and e to the minus that action, on-shell action, is going to be the best approximation to the partition function, ignoring fluctuations around that, like quantum effects. So the partition function set is given by the Euclidean on-shell action as E of our theory, evaluated on a solution to the equations of motion, phi sol, which satisfies this boundary periodicity requirement. So for gravity, if we want to calculate the value of the on-shell action of the Schwarzschild black hole, the Euclidean Schwarzschild black hole, we have a problem because we need to take into account boundary terms. So let me quickly explain where these boundary terms come from. Suppose you have a space M which has a boundary del M. Here, this is a simple example, just a scalar field with a kinetic term and a potential. Obviously, this depends only on phi here and the first derivatives of phi. And you want to calculate the equations of motion, so you calculate this variation. And essentially, you want to bring the variation delta S in a form like this, where you have equations of motion multiplied with delta phi, the variation of phi, so that you can say, okay, delta phi is anything. So the equation, so for this to be an extremal, the equations of motion have to be 0. So this is an expression of phi and its derivatives, and this has to be 0. That's how you derive the equations of motion. The problem is, if you do this variation here, you're going to end up with something like delta of phi prime, the variation of the derivative. In order to bring it in this form, you have to integrate by parts. And on a space with a boundary, that's going to cause a boundary term on the boundary of the space. And in the space of the scalar field, you can show that this term vanishes automatically if you assume plausible boundary conditions like that phi, the value of phi at the boundary is fixed to a constant, or the derivative of phi perpendicular to the boundary is supposed to vanish at the boundary. That's Dirichlet and Neumann boundary conditions. So for the scalar field, this works out very nicely, and this action, so this boundary term vanishes by assuming these kind of boundary conditions, and you get the equations of motion. This means that the variational principle is well defined for this action under the assumption that you have these boundary conditions. And a solution to the equations of motion will be an extremizer of this action. Gravity, in the way we usually write it, is a bit more complicated, because the naive gravity action is written like this. You have the Wiki scalar, and the Wiki scalar is an object that depends on the metric and the first and second derivatives of it. And the problem is that if you want to derive Einstein's equations from this, you need to integrate by parts more often, and you're going to end up with boundary terms here that don't automatically vanish even after imposing Dirichlet boundary conditions, where you say the value of the metric at this boundary of M is fixed. So you still have a boundary term left, and that means you can't quite say something that satisfies the equations of motion extremizes the action, because the value of the action would depend on the boundary conditions. So there's a would depend on the boundary term. So there's a problem. And Gibbons, Hawking, and York found out that you can compensate this by defining the action to be, well, what you always knew. This is the so-called bulk term on the space M, and you add a boundary term that depends on the induced metric of the boundary and the so-called extrinsic curvature of the boundary. If you take this action and you vary it and you do the integration by parts, you get the boundary term from here, and some terms of that boundary term are going to cancel with terms coming from here, and the remaining terms are going to vanish under assuming these kind of boundary conditions. So that means that order for the variational principle to be well defined, you need to add this boundary term. That's the whole story. And this is important because for the Schwarzschild black hole, as I said, R and lambda are 0. So this kind of bulk term, which is just an integral over R minus 2 lambda, would be 0 automatically. But the boundary term gives you a non-zero contribution. So this term here, if you evaluate that on the Euclidean Schwarzschild solution, that gives you a value. In a sense, you have to, there's a certain ambiguity in choosing this term, which you fix by subtracting the result for flat space. Essentially, that's kind of like renormalizing or normalizing this result. And then you obtain that the on-shell action of the Euclidean Schwarzschild black hole is given by this beta squared over 16 pi. Beta is the inverse temperature. So you have this partition function, and you treat this as the partition function for the canonical ensemble at temperature T equals 1 over beta. And from that, by doing your standard manipulations of thermodynamics, you can derive the thermodynamic properties of the Schwarzschild black hole. The energy is defined like this and turns out to be m. The so-called free energy is defined like this. And from that, given that you know energy and temperature, you can read off the entropy, which again turns out to be precisely what it should be. So in a sense, this Euclidean procedure helps you also to derive or motivate these thermodynamic features of the Schwarzschild black hole. And this will play actually a role also in the ADS CFT correspondence, where we'll see that the most abstract formulation of it is in terms of equating the generating functional of the of a dual CFT to the on-shell action or the partition function of the gravity theory in the bulk. But this is something that we're going to then explore in later lectures. And this shows an important thing that you should also remember as your rule of thumb. The temperature of a black hole solution is a geometrical feature of the solution. If I give you a metric of a black hole, then by continuing it into the Euclidean time and making sure there's no conical defect, you can read off the temperature from the metric, from the line element. I don't have to tell you whether that that metric is a solution to the equations of motion of Einstein's gravity or maybe a modified gravity theory. On the other hand, the entropy is not a geometric feature alone. It depends on the value of the action. So if you have a modified gravity theory, which allows for black hole solutions, the entropy of a black hole in that theory is not going to be in general just the area of the event horizon. It's going to be, it might be a more complicated functional. However, there's a paper by Wald and Ayer, I think. They showed that in general, the entropy, even in generalized gravity theories, is always a geometric functional of the bifurcation surface of the black hole. The bifurcation surface, remember, is this specific point here in the Penrose diagram of the black hole where the two event or killing or trapping horizons cross. This is a surface with very, very special geometric properties, and the entropy of the black hole is always going to be a feature of a geometric feature of this surface, not any section necessarily of the event horizon, but of this surface. And that brings us already to the end of the lecture today. Let me see where I was. Gravitational action, yes. So at that point, I would say see you next week, where we start discussing about the information paradox or the information loss paradox of black holes and other thought experiments involving black holes. And of course, are there any questions now? Then I would answer them now. Any questions? Thanks again for your attention. I hope you're all still following and you like the lecture. Let me know if you have questions. Otherwise, have a nice evening and see you next week.